Hi guys, Nicole here with another tutorial. This time we're talking about hexadecimal numbers. So tonight we're going to be discussing what are hexadecimal numbers. First of all, we're going to define what they are, go through some of the basic characterizations, like what makes a hexadecimal number hexadecimal, and then we're going to go through some conversions. So we're actually going to convert, this time we're going to do 392 decimal, we're going to convert that to hexadecimal. So I figure we might as well use the same number, that way you guys can see the relationships between the previous two tutorials. We'll just keep going with this way, and eventually in another tutorial, not this one, but eventually we will go through fractional bits as well. So basically, what is a hexadecimal system? Well, the term hexadecimal means 16, and the reason it's called represents 16 possible values, 0 through 15. So that's why we often designate it with base 16 or with a 0x prefix. So think of it x for hex. That's how, and usually people will say hex. They won't say hexadecimal. They just say hex. So x for hex, and that's where the 0x comes from. As we said before in all the other tutorials, the position of each digit is where it's located in the actual number itself. And then each digit, now this is important, each digit in a hexadecimal system is represented by 4 possible bits. So 4 bits. Now why is that? Well, knowing what we know about a binary system, again, this is I'm just going to draw up here. So we got our least significant bit side over here, going toward our most significant bit side over this way, just like that. Now why is it, why do we do 4 bits per character? It's because if we were to look at, if we turn, let's say we have 1, 1, 0, 1, something like this right here. Well, each of these values is going to have, each of these binary digits has a value of something like this, a scale that's going to look like this. 1, 2, 4, 8. And if we were to add all these values up, 8 plus 4 is 12, plus, so that's 12, plus 2 is 14, plus 1 is 15. So if every single one of these values is turned on, in fact, let's do that really quick. So we're actually going to turn that one. So we're going to do this. Oops. Let's see. I don't know why it's going to pencil. Let's do that again. Okay, there we go. So if we turn all these positions on, that means we're going to add the 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So that gives us 15. But we can't just write 15 like this. And that's where this part here comes from. So again, the reason that we have a 4 bits per value per digit in a hexadecimal system is because if we use 4 bits, we could represent the values 0 through 15, so which is 16 total possibilities. But we can't just write, you'll notice in this little bit here, it says ranging from 0 through 9, and then A through F for 10 through 15. So what exactly does that mean? Well, if we were to look at this number here, we're not just going to say, so if we have 15, for example, so in this case we got 1, 1, 1, 1. Well, if I just write, in a hexadecimal system, we wouldn't say 15. We'd actually say something like this. So we'd say this would actually be 0x and then F, right? Just like that right there, so F. And you might be thinking, why do we do that? Well, if I was to write 1, 5 down like this, hypothetically, let's say I did that, each of these is going to look like this. So you'd have 0, 0, 0, 1 for this value here, and then this one you would actually have 4 ones over here. So, actually, scratch that. It would be like this: 0, 1, 0, 1. There we go, something like that. So you'd end up with 8 bits for the character. And so we need to keep everything on the nibble boundary. We call this here is what we call a nibble. So it's a nibble. And then this whole entire thing, all 8 bits is a byte. That's a byte. So 8 bits is 1 byte. I hope you guys can see this. It's a byte. I'm just going to write that up there so you have it. Very important to be familiar with that, right? All right, so that's what we got. So that's why we do it, because we need to keep that 4-bit. So for each character in a hexadecimal system, we need to keep it on that 4-bit boundary. So in order to do that, we use alphanumerics instead of the actual digits in that case. So for 10 through 15, what we do is we say A through F. And now it's going to look silly. That's totally okay. But what I'll do, and I do this all the time, is I'll literally go like this. So if I know my number is 13, for example, let's say it's 13, I will go like this. I will go 10, 11, 12, 13, A, B, C, D. So just like that. So 15, so I would do the same thing. So 15, it's going to be, so we got 10, 11, 12, 13, 14, 15. That's 6. A, B, C, D, E, F. So nothing wrong with counting on your fingers. I do it all the time. I've been doing this a long time, and I still do it all the time. So no shame. So all right. So that's the basics of it. That's the basics. All right, so we're gonna go back to, so again, so just a little bit of a summary. Each digit is worth 4 bits. Represents the values 0 through 9 and A through F for 10 through 15. So 16 total possibilities. And again, the big thing there is the prefix. So if you have like F like we had before, it would be either 0xF, something like this, or you could also do this. You could also say F and then base 16, like that. You might see this is what you'll sometimes see in calculators. I've seen both, so cool. So there we go. All right, so that's the basics of hex. So now let's see. All right, so now what are some examples of hex? Well, if you've had if you're computer savvy and you've been, if you're familiar with MAC address, the media access control, it's a 6-byte hexadecimal value, and it's what we call a physical address for computers, right? So for things like Ethernet access, right? So that's a really good example. It's a 6-byte field, so 6 bytes. There's 8 bits in a byte, as we just found out. That means it's a 48-bit field. 8 times 6, 48 bits. And also gaming. Where's my gamers out there? So gaming, did I spell that wrong? I think I spelled gaming wrong, guys. How did I do that? It's late in the day. I just noticed that just now. But gaming and computer log files, they'll typically use hexadecimal for the registry codes. So if you've ever seen like the blue screen of death, which I'm pretty sure we've all seen that before, then you're probably familiar with hex. And it's gonna look something like this. It's a pretty easy spot. You might like let's say you get something like this, like FF, FF. 0. Let's say you got something like that for that. That's what your Ethernet might look like, something like that. Or sorry, your MAC address might look something like that. That might be like a MAC address, something like that. And that's hypothetical. And I use the FFs. That's usually broadcast on an Ethernet in the Ethernet protocol. That's usually going to be broadcast. So they use all Fs, and it basically means that all computers on an Ethernet network are listening for their physical address, their MAC address, right? So, but if this is broadcast out right here, this FF, then everybody is going to listen to it and process it. So, because it's for everybody, it's a broadcast, right? So, but they're pretty easy to spot because the alpha. So if you see the letters A through F, usually with numbers, and a lot of times they'll keep it on the boundary, the byte boundary is what we call it. So you can see they do that here. They put these kind of, what they'll usually do is they'll put like a little bit of a space between the two characters. So again, one character is a nibble. So one of these is a nibble. Each of these is a nibble. The whole thing is a byte. But yeah, if you ever see something like that, pretty much stands out like a sore thumb. Now, how do we actually convert these things? Well, so now what we're going to do is we're going to convert 392 decimal, which we've done this in several tutorials now, haven't we? We're going to start by converting it to binary, and then we're going to take that binary value to hex. This is simple, super duper simple today. All right, so you guys ready for this? All right, so what I'm going to do, just like we've been doing all along, I'm going to start by writing my scale. So, 2 to the power 0, because again, we're going to binary. Always remember, always best to go to the simple system. So 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power, 2 to the sixth power, and 2 to the seventh power. And I did use the wrong one again today, so I'm going to have to actually draw some out here. That's okay. I'll just draw this out over here like this. That's okay. A-okay. All right, so then 2 to the 8th power. And what does that give us? 2 to the power 0 is 1. 2 to the power 2 is 2. 2 to the power 2 is 4. 2 to the third power is 8. 2 to the fourth power is 16. We got 32. 64, 128, and 256. There we go. Okay. And then you guys are probably seeing this going like, oh my God, we've done this so many times. So then we're going to say, okay, does this 256 fit into 392? In this case, it does. So I'm going to put a 1 here. I'm going to subtract 256 from 392 and take the difference as the new number. So 392, subtract 256 from it, like so. That's going to give us 6. I should get the same number as yesterday, 136. 128 does fit into that number, so I'm going to put a 1 there. Subtract 128 from it. Take the difference. Gives us 8. And just like before, 64 cannot go into 8. 32 can't go into 8. 16 can't go into 8. 8 goes into itself. Subtract 8 from it. The difference is 0. 0 left over. And nothing can go into 0, so these all become 0. So our binary number becomes 1 1 0 0 1 0 0. I will have that memorized. And then again, just for posterity, I'm going to write it like this: 0 0 0 1 0 0 with a base of 2. All right, so now what do we do with this? Well, so now we want to convert that to hex. So what I'm going to do is I'm going to rewrite this first. So I'm going to come over to a blank canvas over here. So we got 1 1 0 0 1 0 0. So I'm just going to rewrite this up here. So I'm going to say 1 1 0 0 1 and then 0 0. That's right. I forgot I didn't have enough spots. So that's okay. That's totally fine. So again, this will be so now the way this is going to work. This is our binary number. So here we have our binary value. So now today what I'm going to do is I'm going to start over on this side over here, working from right to left. So I'm going to do this from right to left, just like this. All right, so I'm starting over here. And I'm going to break this into 4-bit chunks. In fact, what I'll do is I'm going to change the color here just a little bit, just to make it a little bit easier to see this. And I'll actually make my pen size a little bit bigger. So I'm going to come out 1, 2, 3, 4 bits. And I'm just going to draw a little line down the middle like this. Just to kind of split these up. 1, 2, 3, 4. Just like this. And if we really wanted to, I'm going to put that back to red. We could actually pad some zeros out over here. So we could do something like this. Like 1 more 0 there. Again, this doesn't matter right here because these are just going to be 0 anyway. They're not going to be added. So now again, just like we just talked about a minute ago, each of these is going to have its own value. So I'm going to write the scale up here so we can see it. So 1, remember that's 1 over there because I forgot that I didn't have enough boxes. And then 8. And then this scale is going to reset itself every 4 bits. So 1, 2, 4, 8. And then in this case 1, and we could do 2, 4, 8. Now I do apologize, they're not on boundary. They're not as nice and pretty to see, but you get the idea. So okay, so now what do we do? So just like we do with octal, all we're going to do is add these values up. So it doesn't matter where you start at this point. So I'm just going to add these up. So again, I'm going to add the ones that have the columns that have a 1. I'm going to add these up. So in this case, 8 has a 1 underneath it, 4 has a 0, 2 has a 0, and 1 has a 0. So in this case, it's going to be 8. So I'm going to write that down like this. I'm just going to put this right here. That's 8. In this case, we end up with 1, 0, 0, 0. So same exact number. So here we got 8 down here. And then we have 1 over here. All the zeros are turned off. All the other positions, I should say, are turned off. So we get 1. So in this case, our value, so 392. And I'm going to write this up here so we can see what we're doing here. In fact, actually, let's do that. Yeah. So basically, what does this mean? So how would I write this? I would say 188 base 16, something like this. Or you could do 0x 188, something like this. Again, being careful that x, right, that you're not making it too big. You don't want to go, it can get confused. So x is pretty easy because it's very unique. So it's a little bit harder to mix up, but unlike the O that we did with octal, but that's our number. So in this case, the value 392, so 392 in base 10. In fact, actually, yeah. So that is equivalent to 188 in hex, which was, what did we have yesterday? I think it was, and then it was 610 in octal. We did that in yesterday's tutorial, guys. And then in binary, it's going to be the typical 1 1 0 0 1 0 0 base 2. So all of these are the same. They all mean exactly the same. Pretty cool, isn't it? At least I think so. I think it's pretty cool. So all right. So now, what we're gonna do now is I'm gonna go up one more here. Let's make one more here. Turn all these layers off right here like this. There we go. Okay. There we go. Now we got something going on here. All right. So now let's say we want to take that number to, like, we did the division method yesterday. So I'm going to show you guys the division method with, so in this case, what we're going to go through now is how do we do division method and for today, what we're going to do is we're going to go from decimal, and we're going to convert that to hex. And this is kind of a cool little way as well. So in this case, we're starting with 392 and base 10, and we're taking it to the hex. So pretty cool. So what we're going to do is we're going to do, just like we've been doing, we did this with octal. We're going to do 392. I'm going to write it over like this. And today we're going to divide by, does anybody have a guess what we're going to divide by today? I'll give you a hint. 16. So because we're doing hex, because we're going from decimal to hex, we divide by 16. So easy to remember. So, and I'm going to do my math over here. So long division. So 392. Divide that by 16. What is that? That's going to be 2, which is 32. Take the difference. That gives us 72. I believe this is going to be 4. Let me just double check. 16 times 4, I believe, is going to get us close to that. 2, 4, 5, 6, 64. Yeah, so 64. Okay, so it's going to go 4 times. So 16 is going to go 4 times. It's going to get us close to 72 with 64. Take the difference. And this is going to give us 12. 12 minus 4 is 8. So our remainder is 8. So what we get is 24 with a remainder of 8. We're going to bring the 24 around, just like so. Divide that by 16. And we know that that's going to, all right, so that, again, it gets easier as you go, right? So in this case, 24 divided by 16 only goes once into 24. Take the difference. That gives us, what is that, 8? Yeah. There we go. So in this case, we have 1 with a remainder of 8, just like that. Okay, and then we'll bring the 1 around. 1 divided by 16. One divided by 16. 16 cannot go into 1, so we're going to put a 0 here. So in this case, we get 0 with a remainder of 1. And then, just like we've been doing all along, we're going to read it from the bottom up, just like so. So there, just like magic, this is our hex number. So 0x188, also known as 188 base 16. And that is all there is to that, guys. That is all there is to it. So easy peasy. Now, if we want to go the opposite way, like let's say we want to go hex back to decimal, we could do that too. So let's say we want to go back the way we came. That's actually even easier. So all we do to do that, like let's say we have this number. Now we know our hex number, so this is going hexadecimal to decimal. Like, how do we do this? right? So I'm going to start with my hex number, which in this case is 188 base 16, just like that. And again, I like to write it like that. So what I'm going to do is the first thing I do, just like we've been doing all along, I'm going to convert this to binary first. So we're going to decimal. So I'm going to go 188 just like this. And I try to give myself a little bit of space here. Something like this. In fact, I might change the color here just so I kind of can see what I'm doing. Actually, let's do this. Yeah, that should be good. The crooked lines are driving me nuts. All right, there we go. So I'm going to draw my little scale up. So we're going to go 1, 2, 4, 8. Give myself 8 bits because I know I'm starting as hex. That's why this is so important right here. I know I'm starting with hex, so I'm going to make 4 bits. I know I'm going to do 4 bits per digit. 1, 2, 4, 8. 1, 2, 4, 8. Just like that right there. Okay, perfect. Perfect. All right, and then all we're going to do is, it doesn't matter which value you start with, but I want to make that 8 happen, right? So I'm going to do that by turning the one value, or the 8 position on, and zeroing the other positions out, like so. Same with this one here. So this is going to give us 1, 0, 0, 0, like this. And in this case, all these positions will be 0, and then the 1 is the only thing turned on. So now calculators, a lot of times on your calculators, they're going to omit these zeros over here. So if you ever put this, if you were to do this, in fact, if you're following along right now and you're doing this on a calculator, there's a good chance if you're doing this that you're looking at that value going, where are the 3 zeros at? And don't be alarmed. A lot of times your calculators, they will just omit those zeros over there. So that whether you keep them or drop them, it's irrelevant. But that's our binary number. So there we go. And I'm going to rewrite that up. So we got 1, 1. We got 0, 0, 1, and then 0, 0. Just like that. And then all I have to do now is I could reconvert this over to, so here's our binary number, base 2. If I want to convert this back to decimal now, all I got to do is first identify my scale. So this will be my LSB side over here, least significant bit to most significant bit over here. I'm going to make my little scale here. So we got 1, 2, 4, 8, 16. Work with me, Windows. 32, 64, 128, and then 2, 5, 6. All right, and then we're going to add all the positions that have a 1. We're going to add. So I'm going to add the 256. I'm going to add the 128, and I'm going to add the 8. And if we add all those up, we get 16, 22. I should know these numbers by heart. We get 9 over here and 3. And this is what I like about math is we can always check our work. So that's how we get back to it. So yeah, so that's the basics of hexadecimal. I hope you learned something watching this tutorial. Just like I say with all my videos, practice, practice, practice is key. And eventually you will get good at these things. Again, one last little parting piece of information. Again, the scale for this is going to be like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we're going to go A, B, C, D, E, F. And the more you see these characters, the easier this is going to get. It is a little bit weird at first, I promise. You will get the hang of this. And there are some ones that are really easy. So this is 10, 11, 12, 13, 14, and 15. Yeah, so some of these are going to be easy to spot. Like if you see A is 1, 0, that's on the bottom end. Also, the F is probably the easiest one because it's all ones. So there are some patterns to be familiar with. So, but yeah, hope you guys learned something. And I will see you on the next tutorial. Happy Thursday, and see you on the next one.